So all of you have to prepare our first mid-sem syllabus. The recommended book is this book. Whatever discussion we have done so far in this subject from my part, protection part, is from this book, and you can refer it for mid-sem examination preparation. Today we are going to revise the concepts and the discussion for your mid-sem examination. It starts with the fault. What is a fault and what is the need of the protection? So fault is the flow of current to an undesired or unintended path. We know that. And there are two types of the fault, symmetrical and unsymmetrical fault. So these are the various faults that do occur in different part of the power system. And this fault can cause severe damage to the equipment. That can be either thermal damage or electrodynamic damage. Thermal damage is the deterioration of insulation or breakdown of insulation, whereas electrodynamic damage is because of the repelling forces generated due to high fault current, and it can result into structural damage, okay, which is more severe type of the damage in the equipments. Then most of fault occur in the overhead line, around 50% you can say out of total fault if you consider in the total power system. Then around 50 to 55% of the fault occur in the overhead transmission line. The obvious reason is that the spread of the line is quite higher compared to other number of equipments in the system. Then comes underground cables, switch gears, and then other equipments you can see. And in practice, if we consider the total number of fault, then single line to ground fault is the most common fault. It is around 80 to 90% of the fault that occur in the system are generally single line to ground. Then we have seen another term which is abnormality. What is abnormality? Abnormality is not a fault, but it is a condition. If it remains in the system for a longer period of time, it may result into fault. So what it means that abnormality is not a danger at the beginning, at the initial stage, but if it is not observed, monitored for a period of time, it may result into fault. And what are the examples of abnormality? So abnormality are overloading in all the equipment. Overload is an abnormal operating condition. Then this we will see later on in the specific units. You need not to worry about it right now. Then what is the function of the protective relay? So the function of the protective relay is to open the correct circuit breaker, to disconnect the faulty part from the system, so that there is a minimum or possibly no practical damage to the system or the equipment in which the fault occurs. Also to look after of the protection in case of certain abnormality, to create the fault before system become unstable, so to maintain stability, and to identify the location of the fault maybe. That is required for maintenance purpose. So if we see the total cost of protection, then it covers everything that is relay, panels, wiring, room, CTPT. So the general cost of protection of any equipment in the power system is in the range of 5 to 6% of cost of equipment to be protected. Okay. In exceptional cases, this cost can be more, but this is a general thumb rule that the cost of protection of any equipment should be around 5 to 6% of the total cost of equipment to be protected. Then we have seen the basic tripping circuit. In basic tripping circuit, we know that suppose if we have used one relay here, which is a protective relay. So the relay are classified into two categories. One is called as the protective relay, other is called as the auxiliary relay. Function of main relay or protective relay is that it senses the fault, and once it senses the fault, it will energize the auxiliary relay. The use of auxiliary relay is for announcement, initiations, and other control other control functions like tripping of circuit breaker, or maybe any lamp. Okay, uh, buzzer announcements, anything that can be done using auxiliary relay. So this is a auxiliary relay coil. Now here in this case, this is a main relay. When there is a fault on the feeder, main relay operates, and main relay contact the status. What will happen when the relay trips? When the relay trips, the status of relay contact changes. So here this is a normally open contact, and we know that in control circuit mainly uh, all the control circuit are shown in their de-energized form. So when the main relay trips, the relay contact closes. Normally open contact will close. This is a NO contact here. As it is closed, auxiliary relay coil is energized. So auxiliary relay contact closes. This NO contact closes, and 52A is a mechanical switch which is connected in series with the trip coil of circuit breaker to protect against carrying the DC current for longer period of time. So trip coil of circuit breaker is energized, and it will separate out the circuit breaker contact, and depending upon the quenching medium, the arc formed between the circuit breaker contact will be quenched, and then the breaker will be opened. So this is a basic tripping circuit we have discussed. Now the zones of protection. So question is why the zones of, what is the zone of protection first? Zone of protection is the area within which if there is a fault occur, the given protective system will trip. Suppose here this is a differential scheme which will operate if any fault is occurred between these two CTs. Okay, that is called as the zone of protection. So these are the different zone of protections you can see here. And these zones of protections are overlapped. So if we see here, then this zone of protection is overlapped with this bus bar zone of protection, you can see. Likewise, you can see all the other line protection zone is this one, which is overlapped with bus bar. So all the zones of protections are generally overlapped in the power system, and the reason is that zones of protections are overlapped to avoid blind spot in the power system. What is blind spot? Blind spot is a part of the power system which remains unprotected, and if fault occur in that part, then there is a no protective scheme to operate for it, and then the fault will not be cleared, and practically there will be enormous damage to the entire system because fault will not be cleared. So such part of the system is called as the blind spot. So how we can avoid blind spot? How we can ensure that there is no part of the power system that remains unprotected, and for that we generally overlap the zones of protection. How do we overlap the zones of protection? So zones of protection are overlapped by placing CT at proper places. Okay, so that we ensure that no part of the power system is under any protective scheme. All the parts of the system is covered either in one or two zones. Okay, that is what is the reason zones of protections are overlapped. Then comes the basic requirement of protective scheme. So there are mainly this basic requirements which are also called as the uh, essentials criteria that must be fulfilled by any protective scheme, otherwise that scheme cannot be used. Okay, so let us see one by one. Reliability, it shows the probability of the failure. It shows the quality of a protective scheme. Less is the probability of failure, more is the reliability, we can say. And how we can improve the reliability of a system? So regular and through maintenance, knowledge of the operating person or the system, inherent design feature and fabrication, and this all will improve the reliability of the system. Second is selectivity. Selectivity means it is the ability of a protective system to select and disconnect only faulty part exclusively. Only disconnect faulty part from the rest healthy system, and this should be as minimum as possible. And there are two types of selectivity. Absolute selectivity if is property of a unit protection scheme, and relative selectivity is a property of non-unit protection scheme characteristic. Okay, what is unit protection scheme? It is a scheme which operates for faults within its zone of protection, and it does not respond for any fault outside of zone of protection. Whereas non-unit means it also responds for the fault outside its zone of protection. Okay, both are important uh, as per the as far as the relaying scheme or protection scheme is concerned. Some of the scheme can be unit, some of the scheme can be non-unit. Okay, then comes speed. So obviously the speed of protective scheme should be high such that there is no practical damage to the equipment. Before that, the fault must be cleared, breaker must be operated. And one more point we need to consider here, that speed should not be so high that even the scheme will operate in some transients unnecessarily, like switching transient or lightning transient. Generally, the protective scheme with the time of operation either half cycle or more than half cycle is preferred for instantaneous tripping. Okay, excessive fast tripping is not required. Then next characteristic is discrimination. What is a discrimination? Means the protective scheme should be able to discriminate between fault and load condition even when minimum fault current is less than maximum load current. It means, see, even though fault current is less than load current, it will not create a practical, let's say, electrodynamic damage to the equipment. But what will happen? That is a fault. Current is flowing to an undesired path, and that is a total wastage of the energy that we are supplying. So obviously, and second thing, system may operate in unbalance because suppose there is a single line to ground fault. Although the fault current is less than load current, but the system is operating in the unbalanced condition, and this unbalanced condition is a dangerous situation for a three-phase balanced system. It generates negative sequence current, and which can damage the rotating equipments, rotors of motors or generators. Okay, and that is why it is important, even though the minimum fault current is less than maximum load current, it should operate. And also it should be able to differentiate between similar situations, like whether it is a fault or inrush current or starting current of induction motor, whether it is a power swing, and it should only operate for the fault condition and should not operate for the other. That is what is discrimination. Then comes stability. So stability is the ability of a protective scheme to remain inoperative. This is important under specific conditions. So if a protective scheme is a unit protective scheme, it should not operate for fault outside of zone of protection, and stability is only applicable for unit protective scheme. It is a property of a unit protective scheme that it should not respond to any fault outside of its zone of protection. Then comes sensitivity. Sensitivity means it refers to the minimum level that can be sensed by a protective scheme. Okay, and generally it is referred to the primary of a CT. Transducer is a CT, and it is generally expressed in VA, volt ampere required to operate protective scheme. That is what is the sensitivity. Okay, and last is the economy. As we have already discussed that any protective scheme should not have the total cost of protection which is more than 5 to 6% of the equipment to be protected, except the exceptional cases. Then we have seen this primary protection and backup protection. So primary protection is the first line of defense. That during any fault, this set of relay, the set of relay which operates first and the circuit breaker are known as the primary relay. And in the absence of, let's say, primary relay fails to operate, the relay set of relay which operates is known as the backup protection. And there are three type of backup protection mainly provided. These are called as the relay backup, breaker backup, and remote backup. What is a relay backup? Relay backup is, in this case, all the auxiliary, including CT, PT, relay, everything that is duplicated. Means there is a two set of everything in this relay, and which is very costly. But this type of scheme is used for very critical equipment in the power system, like large generator or large power transformer or EHV lines, where the everything CT, PT, relays, everything is duplicated. Okay, there will be two identical sets. Second is called as the breaker backup. Breaker backup means if it is generally for lines, if let's say fault is not cleared on transmission line, then all the breakers associated with a bus bar connecting to that line will be tripped. And remote backup, which is a widely used protection scheme for transmission lines. In remote backup, what will happen? Relaying towards the source will provide backup to the relaying which is on the downstream. So let's say these are the substations A, B, C, D. Then relay R2, which is at the next substation towards the source, will provide backup to downstream relay. Likewise, R1 will provide backup to R2, and which is a widely used scheme where generally the relay towards the source will provide backup, and which will operate after a discriminating time interval, and will trip the breaker of next line if fault is not cleared at the downstream. Okay, then these are the class types of relays we have discussed. I'm not going into it right now. Classification of relays, these are the set of relays can be classified using different quantities and different constructions, their characteristics, number of quantity they operate, function they perform, and so on. So this was about the unit number 1. Now unit number 2. Is screen visible? Is the screen visible? Unit number 2. Okay, okay. In unit number 2, we have some number of relays that we have studied. So we have started with the thermal relay. What is a thermal relay? The relay which is used to protect against the overload. So what is difference between overload and overcurrent? Overload is a situation where equipment itself will draw more current from the supply. Current is not flowing to undesired path. It is equipment which itself will draw the current, more current from the supply, because it is being overloaded. We are operating it more than its capacity, whether it is a motor, generator, transformer, or any other device. Okay. So overload is a situation where the equipment draws current which is more than its rated capacity, and that is what the current is still flowing in the desired path. Whereas what is overcurrent? Overcurrent is a so in overcurrent, current will be diverted to undesired path, maybe failure of insulation or anything. Okay. Overload can be carried by any equipment for a longer period of time, because each equipment will have a short withstand capacity of carrying the overload. You can see here, this is a equipment characteristic for overload, that it can carry a certain amount of overload for certain period of time, and that depends upon the insulation. So what will happen in the overload? When the equipment draws the overload, the heat generated in the winding will increase at the square proportion. We know that under normal condition also there is a heat generated, which is I square RT. This is the heat generation. But along with there is a heat dissipation, that is a TD raised to 4. The rate is TD raised to 4. The difference between the ambient temperature and the winding temperature. And when the rate of heat generation and heat dissipation balance, the temperature will remain constant in the winding. But when the equipment is overloaded, the heat generation will be at a higher rate, and that is why the equipment will be subjected to overheating condition, mainly the insulation around the winding. And this insulation has a limited capability to carry this overheating or the temperature rise, and after a certain time the temperature may deteriorate and may fail, and which may result into fault. So overload is a abnormality, we can say. Overcurrent is a fault condition. So if the overload is not detected before that, before the capacity of the equipment for which it can withstand it, it can result into fault. Okay, and how to protect against the overload? So here you can see there is a thermal relay. When there is a bimetallic strip, two dissimilar metals connected with each other having different coefficient expansion. There is a heating coil, you can see, which is connected with a CT. So CT is connected in primary is connected in series with equipment to be protected. Secondary is connected with this replica coil. It is called as the replica coil. Okay. So when the equipment draws the current, the same current will be passed through the heating coil, although it is stepped down. But here the coil is designed in such a way that it will generate same heating effect as it is developed in the winding. And that is what is the name is given as the replica coil. It will generate very similar heating effect which is there in the winding. So until the rated current, the bimetallic strip will not bend. But if the current drawn by the motor is more than rated value, the bimetallic strip will bend, and as it bends, the spring operated arm, you can see here, that will be attracted towards this, and then you can see here, from here, the normally open contact closes. So that is given in series with the auxiliary relay coil, and auxiliary relay coil will trip the circuit breaker. So the breaker will be open, and equipment will be released from the overload condition. Fine. The characteristic of the equipment to be protected, the characteristic of the relay will be always, shall be, that must be, I would say, that must be always below the equipment to be protected here, and closely matched with it, so that it will protect the equipment before actually this is the time for which the equipment will be able to carry the overload, and this is the time by which the relay will trip. Okay, so this is called as the overload protection of any equipment. Then comes the overcurrent relay. Overcurrent relay means the relay which operates when the current is more than set value, and they are having different type of characteristics: instantaneous, definite time, inverse time, and IDMT. Instantaneous characteristic means relay will operate if the current is more than set value. Suppose this is the set value. So if the current is more than set value, you can see relay will operate in some specific time with no intentional delay. So instantaneous relay means a relay which has no intentional time delay, which relay generally operate within 1 to 2 cycles. Generally, this relay operates within a cycle. Once the fault occur and current is more than set value, that is called as the instantaneous relay. Remember, okay, relay which operates without any intentional time delay. We are not giving any intentional delay. Second is the definite time relay. These are the characteristic. Understand? In definite time relay also, the relay will operate once the current is more than set value, but it has some specific time delay provided. Intentional delay are provided. Okay. So here in both the cases, once the current is more than set value, the time of operation will remain same. Here it will remain instantaneous. Here it will remain time delayed. Suppose if I set 1 second value, then even current is more than 5 times, 10 times, 20 times, the time of operation is still 1 second. Third type of relay is called as the inverse time. When the current is more than set value, pickup value, the relay will operate, and as higher the current, lower is the time of operation. So it has an inverse characteristic. Okay, higher the current, lower will be the time of operation. And the combination of inverse and definite time is called as the IDMT. For some specific value of the current, it will follow inverse characteristic, and then after it will follow definite minimum time. So this is called as the ideal characteristic. Then these are the terminologies that are used in the relay. Pickup is the electrical quantity which is threshold above which relay starts its operation. Means if the current or voltage or anything, any electrical quantity, it is more than the set value, relay will start its operation. Relay will energize. That is what is called as the pickup. Dropout is the quantity which is threshold below which relay will return to its normal state. So this is about the energization. This is about the de-energization. Operating torque, which will tend to change the status of contact. So normally open contact will become closed. Normally closed contact will become open, and the torque which will act in such a way is called as the operating torque. Restraining torque is the torque which will oppose the operating torque and which will prevent the relay to change its status of the contacts. Burden is called as the power absorbed by the relay circuit which is connected in the CT secondary. Let's say here. So whatever power is absorbed by this relay in VA is called as the burden on CT. Characteristic of the relay is the locus of its pickup or reset. Okay. Then attracted armature relay. Attracted armature relay is one of the simplest relay which is generally used for auxiliary relay, where we have a core, we have wound a coil over the core, and the coil is connected with the CT secondary. When the current passed through the relay coil is more than set value, it will attract the armature, and as the armature is attracted, here normally open contact will become normally closed contact will become open, and normally open contact will become closed, and then this can be used for energizing the trip coil of breaker or maybe any other work. And this relay are instantaneous in operation. It operates within generally one cycle once the current through the relay coil is more than set value. Very simple type of relay. Next is induction disc relay. So there are two types of construction. What you have to write in induction disc relay, if it is asked, you have to draw any one construction, either this or this. Maybe you have to write down about what is the construction, what is its operation, what is its characteristic, if it is asked, and torque equation that we have derived. Anything of this can be asked. So either it has a E-shaped core and I-shaped core in which the aluminum disc is placed. So this is a front view. This is a top view of a disc, or it can have either unshaded and shaded part, shading ring construction. Okay, there is a C-shaped core over which the shading ring is wound. Here you can see current is passed through the relay coil. So this is connected with the CT secondary, this main coil. In this case, when the current is passed through the main coil, it will develop some flux in the core which will also cut the disc. This will also cut the leg coil. So leg coil will produce its own flux which is not in the same phases of main flux but some phase shifted. Both this flux will cut the disc, and interaction of the flux and current which is developed by these two will develop some force, and net force will be the force acting on the disc. But in a normal case, we don't want this to operate. So there is a spring which will hold the disc at the back position, and we will keep it standstill at a position which is called as the backstop. So this is a backstop. This is a moving contact attached with the shaft with rotating disc, fixed contact. So when the force developed by the current and interaction of the current and flux is more than spring torque, disc will rotate in the opposite direction, and moving contact will hit the fixed contact, and that is we call as the relay is operated. So this relay operates when the operating torque is more than restraining torque. Operating torque is developed by the interaction of flux and current. Restraining torque is developed by spring. Okay, any doubt? In another case, here we have used a shading ring principle. So the use of shading ring is to develop the phase shift, because single phase flux will not be able to rotate the disc, which is held back by spring. So this is the torque equation. The current both the flux developed in the core can be shown by these equations, and interaction of the flux and current with each other will develop the force, and that force is phi 1 phi 2 sine theta, which will develop on the disk. When the force acting on the disk is more than set value, sorry, more than the spring value, disk will rotate and moving contact will hit the fixed contact. Okay. Now this relay have two settings. One setting is called as the plug setting. Plug setting is defined as the percentage of relay rated current, and which will decide the pickup value, which will decide the threshold. So to operate this relay at different current values, and generally the tapings are provided on the main coil, and these tapings are taken outside the relay panel, and you can select number of tapings that can be connected in series with the relay coil. So as the phase relay will have a plug setting of 50 to 200% range, which is generally for a 1 ampere rated relay, 0.5 to 2 ampere pickup is provided. If we select 50% tapping, all the coils of the, all the turns of the coil will be connected in series with CT secondary. And if we want relay to operate at higher current, number of turns will be reduced. That is connected in series with the relay coil. Depending upon the plug setting, we have two different relay, phase relay and ground relay. Ground relays are generally more sensitive compared to the phase relay, because during ground fault, the fault current is limited by number of factors, which includes the tower footing resistance, arc resistance, ground resistance, deliberate resistance connected in the neutral of generator or transformer, and further the zero sequence impedance of the transmission line, which is 2 to 3 times the positive sequence. So generally the ground fault current in the transmission line is much lower. Second type of setting is called as the time multiplier setting. So time multiplier setting is generally used to decide the time of operation, and the range is from 0 to 1. Okay. Time multiplier setting is adjusted by adjusting the black dial, that will adjust the position of the backstop. So as the position of the backstop is adjusted, we can say that the moving contact position is adjusted, and therefore the distance that is traveled by the moving contact will be changed. And this is how the time of operation can be changed. Based on the TMS value, relay may have different characteristics for each TMS. You can see here. And generally, the time of operation of a normal inverse characteristic is given by this equation 3 upon log PSM into TMS. Okay. What is PSM? PSM is a ratio of fault current to the pickup current. PSM, no, Nidhi, it is not required if it is not asked. If it is asked that what do you mean by plug setting and time multiplier setting for an overcurrent relay, then you have to mention it. Got it, Nidhi? Okay, fine. What is PSM? PSM is the ratio of fault current to pickup current, and generally the relay characteristics are given in PSM versus the time of operation. Why? Because in different part of the power system, fault current will be different, and if we explain, if we want to describe the characteristic using fault current, each relay depending upon its application will have different characteristics. So to make relay characteristic independent of the actual fault current and pickup value, generally the plug setting multiplier is defined, and the relay characteristic are generally given in terms of PSM versus TOP. Okay. Again, I am saying PSM is not a setting; it is a term which is used to describe the relay characteristic. Okay. Apart from normal inverse characteristic, there are two other characteristics of this relay will are also used, which is called as the very inverse and extremely inverse. Very extreme inverse characteristic is more steeper than normal inverse, and extremely inverse even is 1 degree more steeper than very inverse. You can see extremely inverse characteristic is having high time for low current and low time for high current. So application of this we have seen in the radial feeder protection. And these are the terminologies you should remember: resetting time and overshoot, over travel. Resetting time is the time within which it will come to its normal state from the fully operated state, and overshoot is the distance it will travel even though the supply to the coil is shut off due to the distance it will travel due to momentum of the disk, moment of inertia. So this is was about the induction disk relay. Then comes the induction cup relay. In induction cup relay, we have a 4-pole or 8-pole structure over which the two coils are wound. One coil is fed from voltage coil which is fed from PT from the bus. Another coil is a current coil which is fed from CT. You can see here. Both this coil will set up its flux in the core, and this flux will interact with the cup. There is a cup, a hollow cup mounted over the shaft, aluminum cup, and there is a moving coil attached to the cup, a moving contact attached to the cup, which is held back by backstop, and there is a fixed contact. The distance between moving and fixed contact is very small, and in this relay, there is restraining torque is developed by the current direction itself. So what is the operation of this relay? That under normal condition, the use of directional relay is that it is used to identify the direction of fault, whether the fault is in forward direction or reverse direction. Because in power system, sometimes it is required to identify the direction of fault also. And then this type of relay is used where the direction estimation is required. So in this case, the flux developed by, you can see, voltage coil which is fed from PT will leg the V by 90 degree. The current coil develops the flux in the core which is in phase with the current of the current coil phi I. And there are two flux different, phi I, phi V, and the angle between them is alpha. So this is the torque developed by. Now phi V is proportional to V, phi I is proportional to I, so we can write II and sine 90 minus phi. Instead of alpha, we can write this. So torque is nothing, Vi cos phi, and this relay will operate when the angle change by more than 90 degree, and this will happen when actually current is reversed to the relay coil. Voltage cannot be reversed because voltage is taken from the bus bar voltage will remain as it is, and when the current is reversed through the relay coil, the torque developed will be negative and relay will trip. So this relay cup will move in the backward direction for one direction of the current, and it will reverse its direction when the current is reversed to the current flow. Here you can see. This is the directional relay characteristic. You can see where for this 90 this equation you can see the torque developed will be positive in this region when the angle is between plus 90 to minus 90, and it will be negative in this region between this. Now this relay has a problem which is called as that as the relay requires two flux phi V and phi Y to develop. Phi I will be there in most of cases, as the current is more than set value, phi I will be more. But if the fault occur very near to the bus bar, suppose this is our directional relay. If the fault occur very near to the bus bar voltage will collapse, and therefore sufficient voltage may not be available to voltage coil of this relay. Therefore, phi V developed in the core may not be sufficient to develop some torque which can rotate the cup. So the relay will not operate. So this voltage is called as the minimum polarizing voltage, Vp, which is the voltage required for minimum voltage required for this relay to operate. And in the absence of polarizing voltage, relay may not trip. That is called as the dead zone. So this is a dead zone. So the distance within which if fault occur and sufficient polarizing voltage is not available, so that distance is called as the dead zone for this directional relay. Okay. Generally, the directional relay maximum torque angle can be changed. Here you can see that the torque developed is maximum for phi is 0 degree. But in practice, this phi can be different for different lines, short line, long line, and probably medium line. And therefore, the maximum torque angle can be changed in this relay. So the characteristic will change. Then comes the differential relay. So differential relay is a relay which will compare the current entering into the winding and leaving the winding. And when the current entering and leaving the winding is not the same, the differential current I1 minus I2 will flow through the relay coil. Okay. So this is called as the circulating current differential relay because under normal condition, the current will be circulated through the pilot wire. However, the current difference to the relay coil will be zero because both the current will be same. And even during external fault condition also, this current are expected to be the same and relay should not trip. During internal fault, the current entering to the winding and leaving the winding will not be same, and hence a differential current is passed through the relay coil. And if this current is more than set value, pickup value, relay will trip. Generally, this differential relay are instantaneous in operation. Okay. What are the requirement of a simple differential relay? That relay must be connected at equipotential point. Under normal condition, voltage across the relay coil from both the ends must be the same. Pilot wire length must be same. What is a pilot wire? These are the wires which connects CT secondary to the relay coil because generally CTs are placed near the equipment, whether it is a generator or transformer or motor, whereas the relays are placed in the control room. So the wires connecting CT secondary to the relay coil are called as the pilot wire. So the length of the pilot wire must be same. Relay must be connected at the equipotential point. CT polarity must be connected in a correct way, and CT should have the identical saturation characteristic. But what is drawback with this relay? That generally both the CT, even if you take from the same manufacturer, may not have the same identical characteristic, and that is why there is a some current which will flow through the relay coil due to CT error. That current is known as the spill current. Small current that pass through the relay coil under normal condition due to CT error or unidentical CT characteristic. Now during external fault, due to large CT error, if this field current is more than set value, then this relay will trip. And this is a unit protection scheme. It should operate for winding fault only. So if it operates for external fault, this is not a stable. It does not fulfill the stability criteria, and that is why this type of relay are generally not used. Then the drawback of simple differential relay is overcome by bias differential relay, where we also put one restraining coil, and current through the restraining coil will be total. If we take n turns, then this current is I1, this current is I2. So this is called as the average restraint current or restraint MMF. So average restraint current is nothing I1 plus I2 by 2, and this relay will only trip when the ratio of pickup current to average restraint current is more than set value. This is called as the percentage bias. So during external fault, as both the CT will carry the current, numerator will be lower, denominator will be higher, and percentage bias will not be satisfied even though there are large errors. And during internal fault, only one of the current will increase, the other current will be lower, and that is why the CT ratio, the percentage bias will be satisfied. And in this way, bias differential relay will remain stable against the external fault. This is what we have seen. The characteristic of bias differential relay, you can see this is if the ratio of I1 minus I2 by I1 plus I2 by 2 is more than set value, it has a slope. So this is a bias slope. Relay will trip, and otherwise it will restrain. Okay. Then the last relay that we discussed was about the opposed voltage relay, in which is generally used for the small feeder. This relay cannot be used for small feeder. Why? Because or the transmission line, because here the cities are placed at let's say there are two substations which are separated by 50 kilometers. So we have to put one CT at substation A, other CT at substation B, and relay should be put at somewhere at the midpoint 25 kilometers. So we need one substation in between to just put the relay. Moreover, the length of pilot wire, so cost of protection will be very high. Sensitivity of the protection scheme cannot be guaranteed because there is a large drop on the secondary side, and that is why these schemes are generally not used. Pilot wire protections are generally not used for transmission, whereas this is used for the small feeder, where actually you can put relay at substation 1, relay you can put at substation 2, and under normal condition, as the CT polarity are connected in opposite way, the voltage across both the secondary will be equal and opposite, so there is no current passing through the pilot wire under normal condition and even under external fault. But in this case, as the secondary does not induce any voltage under normal case, primary is energized. The core of the CT generally preferred is called as the air core. Otherwise, what will happen? The core will be saturated because under normal conditions, CT secondary voltage is zero, which is you can say here equal and opposite. So the CT secondary current will be zero under normal condition, and which is like an open circuit. Not the voltage, current will be zero. So here this is can be used for the small feeder, which is called as the opposed voltage differential relay. Okay. Then we have seen the overcurrent protection of transmission line, where we have considered three line sections different, and for which we have seen the overcurrent protection of transmission line. There are three schemes which we discussed. We have discussed current discrimination, time, and current time. I will quickly go through it. Time is very less. In current discrimination, we use instantaneous relays, and pickup of this relay are more than, let's say, pickup of relay R1 is more than R2 is less than more than R3. Their time of operation are same because they are instantaneous in operation. Okay, but what is drawback? There are many drawback that they are not able to discriminate between the end zone fault. Relay will overreach. It does not provide remote backup because the pickup of relay are greater than the downstream relay, and therefore they will not provide backup. They are affected by ZS by ZL ratio. ZS is the source impedance from let's say source point to the relaying point for this relay, and ZL is the impedance from relaying point to the fault point. They are affected by DC offset. Suppose the fault is in the nearby line section, but due to doubling effect, if the fault current looks like double, which is more than pickup of this relay, so the relay will operate. So they have a problem with the DC offset. So generally they are not set up to 100% of the line length, and this due to this discrimination, problem due to current discrimination, this scheme is not used. Then comes time discrimination, where we use the definite time relay, where the pickup of all these three relay will be same, but their time of operation are different. R1 is R2 is R. But the only drawback, it will provide backup. They are not affected by DC offset, not affected by transient overreach issue, not affected by ZS by ZL ratio. But the only drawback here, that as you move from load to source, the time of operation of relay will increase, and therefore the fault which is very near to generator, which is the most severe fault, will be cleared in the slowest time. So heaviest fault is cleared first. And to overcome this problem, generally the scheme which is used is called as the current time discrimination. Here we have used DMT relay. Okay, these are DMT relay. Previously, these are instantaneous relay. And then we use IDMT relay. So these three relays are IDMT relays, group of relay. And the relays are set up to the end of next protected zone. And as the current is higher, the time of operation is lower. So the drawback of previous time discrimination is overcome, as well as it also provide backup to each other, and therefore the drawback of time discrimination, current discrimination is also overcome. Only problem here that when there is a very high ZS to ZL ratio, which is generally for the end section case, so the solution to this problem is that for the end section we use extremely inverse or very inverse characteristic, so that we have sufficient discriminating interval time for the end section fault. So this is the application of EI or VI, that either because of the very high ZS to ZL ratio, fault current in the line section will vary not very significantly, and therefore The characteristic which is suitable for the end section fault, end section protection are either EI or VI. Moreover, EI or VI characteristic is also closely matching with the MCCB characteristic, so it will give better coordination. Then rules, you need to remember the rules for examples. I'm not going to discuss the rules. And this things we have conceived, we have discussed that how the earth fault relays are connected. Earth fault relay can be connected either in the residual circuit of 3-line CT, where the residual current, that is IA plus IB plus IC, will flow through the relay coil, or it can be connected in the neutral point of a grounding transformer, neutral grounding transformer. So this is the earth fault relay. Or it can be connected across CBCT, core balance CT, CBCT, where a coil is wound over the core and the relay is connected across it. Okay, so these are the three possible type of connection. When we require more sensitive relay setting, it can be either connected across neutral CT or CBCT, because if it is connected in the residual circuit, the magnetizing current of the 3-line CT will not allow you to set it more sensitive in that case. Okay. Then two overcurrent one earth fault scheme, in which we have put two phase relay in two of the line and one ground relay in the residual circuit, and it will protect against all type of fault. And you can see the control logic is connected in parallel. So any of phase or ground relay, when operate depending upon the fault, will energize the auxiliary relay and it will trip the breaker. The only problem with this scheme is that when there is a delta star transformer in between, in between the substation, any line to line fault on star side will create will circulate double the fault current on one of the phase on delta side. And suppose in that phase, if we have not put the relay, then possibly the this phase circuit will get some damage, may have a practical damage. And that is why in such scheme, 3 overcurrent 1 earth fault scheme is used when there is a feeder having a delta star transformer in between. Let's say here. So here there is a load. So this can be 2 overcurrent 1 earth fault scheme, but this has to be 3 overcurrent 1 earth fault scheme because of the delta star transformer. Okay. So here we also put one more relay, and here we put the normally open contact of that relay. So up to this point, we have kept in our mid-sem. Okay. So any doubt from anyone? One more point I would like to add, that we have a protection as well as we have a switch gear section. So normally the weightage of both the sections, switch gear and protection, will be generally equal. So don't think that you will only prepare one part, either protection part or switch gear part, and you can score good marks. Normally, the weightage of both the parts, switch gear and the protection part, in this mid semester will probably be equal. Okay, I hope you understand. Apur, I will check it and will let you know. Okay. Now, any question from anyone? Clear? So I wish you all the best. Prepare well, because this is your final year, and the mid-sem component can significantly affect your final grade in the subject. And syllabus is not that much lengthy right now for mid one. Comparing, if you compare it to the overall syllabus, so I hope that you will prepare well and you will perform well. Most of point I have discussed today, whatever is the syllabus till now we have covered, and I hope that it will help you to prepare for the mid-sem. Okay, so I wish you all good luck, and wish that I hope that you will perform well. So with this, you can enter your enrollment number and you can leave the chat box. Okay, thank you everyone. Okay, with this I'll end the session. Thank you, everyone.